Okay, good afternoon, everyone. My name is Shizhu He, and I'm come from the National Library of Pattern Recognition Institute of Automation, Chinese. And I'm come from the Chinese Academy of Science, and in this talk, I will introduce my paper with the title "Question Answer over linked data using physical logic." Let's begin. The first part is the introduction. Okay. With the rapid development of the web of data, there are more and more linked data published with the RDF dataset in the web. And in those linked data, there contain wealth of endowment knowledge, such as these music brands, and including some open structural knowledge base, such as Wikipedia, Yago, and Freebase. Those structured data contain a wealth of knowledge, and including some entity classes and the relation between entity and classes. And those structured data could aim to benefit the AI and NLP. However, how can we assess it? In the linked data or the RDF datasets, the standard language to query this dataset is the Sparkle. Traditional, if one want to assess those structured data, they used maybe they will need the help of experts and developers, and they transfer the natural language queries into those Sparkle, and those structured query will evaluate in the linked data could obtain the result, and those results could satisfy with those information need. However, in this tradition, it will hamper the common users between the common users and the linked data. On the one hand, if one will assess those linked data, they must be familiar with the vocabulary used in this linked data. And on the other hand, he must familiar with the Sparkle, and those hamper the common users and the linked data. Is there exist another better way to assess it? The question-answer system is a better way, we believe. And the question-answer system will focus on assess those linked data directly. And the most popular way of question-answer system is convert or translation the natural language question into the Sparkle directly, and then evaluate those Sparkle over the linked data, and retrieve the answer to these questions. The standard method in the question-answer system in this task is adopting those pipeline system. At first, with regarding this question, we must know the key phrase in the question, and such as in this question, we must know the software founding place California is the key phrase in this question, and then we must know the semantic items in the linked data which corresponding the phrase in this question, such as we must know this founding will map to the founding place in the structured data, and we must know the organization is mapped to this maybe it's the state of California or film California. And then we have those mapped semantic items. We should group those semantic items into semantic triples. And then with those semantic triples, we could generate the sparkle. This is the traditional math. And however, this system is not, to fulfill this task, it's not that easy. Because the three mentioned steps used in this pipeline system will face the question of ambiguity, such as in the question decomposing and the phrase segment, we can choose California and California, USA. So it is have the ambiguity. And when we mapped the phrase to semantic items, the phrase California could map to the state California or film California. And when we group in the semantic items, the mapped semantic item software could match with those two semantic items is property, and this semantic item is class. And this software could match with producer and also could match with the developer. How can we choose it? In the traditional way, they address the ambiguity, adopt a pipeline math. So we consider, can we make a joint discoverability? That is, we believe that the three steps will have multi effect with each other. So the first question we want to answer is, can we make joint disambiguation? And then the traditional math will adopt a manual design pattern to resolve the problems in the upper three steps. For example, the first one will map the phrase into single items using many rules, such as if the phrase is a verb, they will map to the property. In this question, who produces the most film? The product will map to the property produced. And in the first two, the system is called dinner. They group the semantic items according to the dependent paths of phrase in the question. They used three patterns, such as in this question, they based on the phrase in the question, such as you can see the code is web, and who and Scarface is his argument. And they will based on this dependence path, and the mapped semantic item based on this dependent path. So the code is mapped to this property. So we wonder, can we automatically learn the rules and patterns? And based on those two questions and two considerations, we adopt pattern learning structure to learn the patterns. And we designed several mental patterns. Those patterns could not cover the three patterns mentioned above. The mental patterns can generate all syntactic paths, and those spanning paths could be benefit to grouping the semantic items. And in other hands, we perform the joint inference with a joint model. We formulate the knowledge for resolving the disambiguity as a first order logic and put them in the Markov logic network to model this joint disambiguation. We know the Markov logic network is a statistical rational framework which combines the first order logic and Markov network. A Markov logic network is a set of pairs, and F is a formula in first order logic, and W is a real number. It is the weight of the first order logic. And the Markov MLN, together with some constant, it will define a Markov network. In the Markov network, the node is the grounding atoms in the predicate, and the feature of each grounding of each formula is the click in the network, and it is with corresponding weight. And the probability of the word or the choose value of all inference result is probability to the sum of weight of formulas it is satisfied. That is said, if the inference result satisfies more formulas, and the probability is larger. And based on this consideration, we introduced our math. Towards the three steps mentioned above, we designed three hidden predicates, such as the has phrase. As phrase I indicates that the ith candidate phrase has been chosen, which indicates that we want to choose the phrase and not other phrase. And the phrase ij will indicate that the ith phrase is mapped to the j semantic item, which corresponds in the second task, semantic phrase mapping to semantic items. And the relation indicates that the semantic items i's and j's can be grouped together with the argument match type. We defined 4 types of argument match, such as in this question, which derivation shows were created by Walt Disney, and the created by were mapped to the character. Walt Disney is object of the character, so their match type is 2 minus 1. And we designed several observed predicates which describe the attribution of phrase and the attribution between the phrase and semantic items, and the relation between semantic items and some others, such as in this observed predicate will indicate such as phrase post tag will indicate that the phrase P has the post tag of PT, such as shows has the post tag of NS. We have this observed predicate, and we with the framework of MLN, we designed several formulas to resolve the disambiguation. The formula including 2 types. The first type is the Boolean formula, and the second type is weight formulas. The Boolean formulas is the hard formula. That is said, the inference result every atom should satisfy all of the hard formulas. For example, this hard formula will indicate that every phrase should map to at most just 1 semantic items. That is said, if we know the California may be mapped to the state California and film California, but in the inference result, we should choose just 1. And the weighted formula is the matter pattern that's mentioned above. Those mentioned formulas will weighted the inference result, such as in these weighted formulas, it is corresponding the association between the POS tag of phrase and the semantic items type of the mapped semantic items. Such as if we have this is the POS tag of phrase. If we have two type of POS tag, and this is the type of semantic items. If we have 3 types of semantic items, we will generate 6 specific formulas, and the plus sign here is to indicate that we should generate and weighted the formulas separately. Okay, let's review the framework or question answer system, and to translation the natural language question into the Sparkle, or we call the structural queries. We will follow those steps. At first, we will analyze the question. This including we will detect the type and detect the focus and others. And then we should detecting the candidate phrase and finding the candidate semantic items which match with the phrase, and extraction other features from the question and from the knowledge base. And then, with the predicate and formulas, we using the MLN to join this combination. The inference result, based on the inference result, we could generate the query graph. The query graph will generate the final Sparkle. This is the framework or system. And next, we will introduce the experiment. We used 3 colleges of questions from QLD to evaluate our system, and we used QLD3, the training set of QLD3 to training our model, and the new data is Wikipedia and Yago. And to perform the inference and knowing the weight of MLN, we used the BEAST toolkit. To demonstrate the effect of joint inference, we designed the pipeline system, which independently performs the phrase detection and the phrase mapping and the mapped semantic item grouping. And this line is joint effect, and this line is pipeline effects. And from this table, we can observe that in the final result, the joint model will outperform the pipeline model. And in the every step, almost, the joint model will outperform the pipeline system. And then we will demonstrate the effect of pattern learning. The dinner system, they used human designed rulers to group in semantic items, and we do not use any human designed patterns, and our system could cover, and the sharp Q is the question the system could address, and the sharp A is the question we could answer correctly. So in this table, we could observe that we could cover or we could answer more questions than dinner, and the performance is better. To better understanding the pattern learning, we sample the weight of formulas. Those formulas will corresponding the lower formulas. in this table, we could observe that the pericycle NN will map to the entity more likely to the classism property. And the web phrase will more likely map to the property, we compare our system to the state of our system. Those systems will participate of QAD benchmarks, and we could observe that our system have competitive performance. And the last is the conclusions. In this paper, we propose a math for question-answer over linked data, which could resolve the ambiguity in every steps into a unified model with the Markov logic network. And the proposed math with this model could name effect patterns for the grouping items, and instead of human-designed patterns. This is our work. Thanks. Yeah.
Thank you very much. Any questions from the audience? The weightings that you had on that slide 38, 30s, there. So those weightings were created by the beast, or where do those weights come from again?
The weight is
yes, in table 7, yes.
Such as the weight will generate. We used the training data set to generate the specific first order logic, and the weight is corresponding the first order logic. And to these formulas, we will generate many specific formulas, and the weight is penalty. The penalty of these formulas. If the inference result will satisfy more the formulas, and the weight is higher, and the probability of the word is higher. So in this way, we could observe that the higher of the weight will indicate that the association is more likely. We could observe in these three names. The first line is largely, so we could find that the NN phrase will more likely map to the entity instead of classing the property.
Okay. Question over here.
Hi, thanks for the talk. You have 3 hidden variables.
Yes.
So I'm wondering, when you're learning the weights for each formulas, do you have annotated data for each hidden variables?
Yes, we used the training dataset of QAD3 to training our system, and to generate the specific first order logic. We have the training dataset, and the hidden
So the hidden variables from the phrase mapping, the mapping from the phrase to the semantic items and the relation between the semantic items. So all of them are gotten from the training data.
We designed by ourselves, human design. We label.
Oh, you have the human to label
yes.
all of these mappings?
Yes.
I'm wondering, is it possible to treat them as all the hidden variables, because you have your natural question, right? Natural language, your
yes.
question represented by the natural language, then you have the final answer. Then you don't need the human annotation. You can generate all the possible combinations.
Yes, it is a problem. So we want, in the future work, we will make the hidden predicate with a hidden variable.
Yeah.
we just have 110 training data set. So,
Okay.
so we can label. And if we want have better performance, we should more training data set. And we believe that it is impossible. So.
Will you be participating in QALD4 or 5?
4, 3 and 4.
So you're participating in it?
Yes.
Okay, well, good luck.
Okay, thank you.
Once again, I want to announce that let's thank our speaker one more time, excuse me. Thank you.